Hi, my name is Paige, and welcome to my presentation on Stephen Arthur Cook. Stephen Cook is a famous computer scientist and mathematician who has made significant contributions in the fields of complexity theory and proof complexity. Cook was born in Buffalo, New York in 1939, where his father was a chemist and part-time professor, and his mom would occasionally teach English at the local community college. Cook attended undergraduate at the University of Michigan. He went in with his degree as science engineering, but soon changed it to mathematics, which is where he found his passion. After graduating and gaining his bachelor's degree, he went on to get his PhD in mathematics at Harvard University. Here is where he started his research and gained interest in computational complexity. This experience laid the groundwork for Cook in his coming years, where he made his most well-known discovery of NP-complete problems. Now, to give some context and background information, P problems can be easily solved in a reasonable amount of time. And NP problems, on the other hand, are a little more difficult, but still can be verified and solved in polynomial time. NP-complete problems are fundamentally different and can't be solved in a reasonable amount of time. There are a subclass that contains some of the hardest problems in the NP set. An example would be the traveling salesman problem. So let's imagine a salesman. That's his work. He has to travel to a small number of cities, and he wants to go the shortest path that'll get him there and back, so he has to spend the least amount of money. And initially, this problem doesn't seem that hard, and with a very few number of cities, it's not. But as you increase the number of cities he's traveling to, the number of paths grow exponentially. And they grow so fast that it would take the computer an infinite amount of time to find the shortest distance. And there are numerous other problems like this that would require just an unrealistic amount of time to solve. However, if we could find a solution to just one of these problems, we would have the solution to all NP problems. And this is essentially what Cook discovered. So if just one of the NP-complete problems is also NP, or could be solved in polynomial time, then they all are. Then we could say that P equals NP. But if just one of the NP-complete problems is not NP, could not be solved in polynomial time, then none of them are. So he's saying that there's one key for all of the NP-complete problems, one key that fits into all of them. And if this one key can unlock one of the problems, it unlocks all of them. And if this one key can't unlock one of the NP-complete problems, none of them can be unlocked. And so currently they're still all locked, and we do not have a solution that would get us to P equals NP. And that's kind of the analogy that floats around the term. So currently, NP-complete problems play a pivotal role in the study of algorithms and computational complexity, particularly in the field of artificial intelligence. Understanding and identifying NP-complete problems are crucial for developing efficient algorithms and for devising strategies to tackle these complex computational challenges we see in AI. So what if P equals NP? Well, it would provide answers to a large number of concrete problems we have in our world today. Some of these improvements or solutions can be seen in this list, but it is just a small example of what would be changed. So first off, we have circuit designing. Minimalization for circuit designing could be easily done. Large Boolean circuits are solved based on approximations. Hardware dependency can be largely reduced if circuit solving can be easily computed. Next, we have compilers. Most compilers use graph coloring for register allocation in their architecture. The register allocation will be optimized to include a large number of registers for storage. The existing solutions we have right now provide approximate solutions, where an exact solution would mean faster processing to a great extent. And lastly, we have plane ticket booking. Distance modeling is an important factor to be considered while booking plane tickets or train tickets. Um, if P equals NP, then it would be possible to find the optimal sequence of points to follow while visiting the cities. It would be easy to have the cheapest sequence of flights that visit some number of cities ending at a desired city. So overall, P does not equal NP today. We do not have that golden key that unlocks the door. However, this remains one of the most important open questions in the fields of computer science and mathematics, and it just shows how big um, of a finding this was for Stephen Cook and how much of our foundation of mathematics could be changed with this one solution.